Okay, so what we did last class was to take a look at the impedance tube technique, and we have the solution, and we constructed a general expression for the amplitude and phase for travelling waves, and then we took a look at how the solution here is the amplitude and the phase distributions, how the solutions were for various values of admittance, and we looked at how things will change for real part of admittance, and we also looked at how things would change for the imaginary part of admittance. Now the next thing to, I mean, if I were a mechanical engineer, I will be very satisfied with this, because I know how much power is absorbed or how much power is given out, and I will leave it here. But working in thermoacoustics, you have to worry about stability, so that is the big issue here. So our job is to predict stability from this information we obtained. So I think what I will do is to give a simple example where we can try to connect the links between the admittance and the stability. I will just give a small example, but it is not like this is a representative example or something, but you can try to see what happens, and from there we can maybe do more complicated problems in the examination or something. Okay, so just to emphasize, we said that omega, the frequency, or we call it also eigenvalue. Eigenvalue means the unique values for which there are solutions. So this is complex in general. So let me ask somebody. Yeah, Deepak, you are Deepak, right? So what does the real part of omega mean, and what does the imaginary part of omega mean, or should we use both, or should we use only the real part?
For the amplitude part, we go for the real part.
For what?
Amplitude.
And what does the imaginary, what is it used for? Manoj, what?
User phase.
Yeah, the omega imaginary indicates the growth or decay of the oscillations, and omega real indicates the periodic part, and I have spoken about it already, but let me just emphasize it again, because this is perhaps the most important thing in this class. So omega equal to omega real plus I times omega imaginary, so E times I omega t equal to E times I omega real t times E times I times omega imaginary t. I times I is minus 1, so we can rewrite this as e power I omega real t times e power minus omega imaginary t. So this is the periodic part, this is the growth or decay. And we saw from acoustic analogy that if energy is coming in from the boundaries, acoustic oscillations, the net energy of the system, acoustic energy, whatever we called acoustic energy, can grow, or if it goes out of the system it can decay. So now we need to look at how you can work this out in, that was in a hand waving sense, but can we get expression for this growth rate or decay rate. So that is the next thing that we are going to look at. We looked at a problem of a simple pipe which is closed at both ends, and did you get any growth or decay for the system? We did not. So we got real eigenvalues, right? What are the eigenvalues for this system? Yeah, n lambda by 2. So you had to fit multiples of lambda by 2 in this in the pipe. So the frequencies went like NC over 2L. The frequencies were going like NC over 2L, which is a purely real number. So that means if you could manage to set up oscillations in a pipe somehow mysteriously, we could do it by connecting a loudspeaker, keep it on, and then at some point you turn the loudspeaker off, and then the oscillations will continue to stay there forever. In reality it does not exist, right. I mean, you can try to do this experiment, there will always be losses. So let us think of a system where there are small losses, and small losses help me to do the algebra easily. In reality the losses can be big as well. So this is a problem, and I have a companion problem in which I have perfectly closed here. So somehow magically I have a perfect end, you have a perfectly rigid huge block being cemented here or something, and I have this pipe of same length, but let us say I put a small hole or something. So it is almost closed, but there is some small admittance. So here you have velocity exactly 0, u prime equals 0. Here I will have u prime is small, so some amount of sound is quote unquote leaked out to something. So we will not worry about what happens when the sound is leaked out to the outside, we will just restrict to what is inside in terms of the admittance, and then we will try to link that with the growth rate. That means the problem is, in this first problem, when I have perfectly closed conditions, if I have some oscillation there, let us say I have oscillations with amplitude 10 pascals or something, and if I do not turn on the speaker, I just leave the oscillation at 10 pascal, it will continue to stay at 10 pascal forever. But if some amount is leaking, will the 10 pascals come down? It will die down slowly. What is the rate at which it dies down? So from this framework it seems like we can fit the exponential decay to it, and then how would you relate that to the whatever is leaking out. On the contrary, if you had a flame, let us say we have a small flame and the flame amplifies the incoming disturbance, then you can have a growth, and let us say the flame is a small disturbance, amplifying it a little bit, then can you find expression for the growth rate in this case in terms of the admittance of the flame. So that is the question. I hope the question is clear to everyone. Okay. So we need a solution, and we have the solution for pressure, which is from a e power ikx plus b e power minus ikx, and we know by now how to get the expression for acoustic velocity, which is, or the particle velocity, which is by using the linearized momentum equation or momentum equation for small perturbation. So you get the velocity and then apply the appropriate boundary conditions, right? Yes, Vishnu.
Yeah, for acoustic velocity we generally take it as adiabatic traveling waves, but when we add energy there is that velocity will change, no?
That is, if you are talking about a small particle and if you are being able to add energy as in by heat energy or something to the particle, but we are not speaking about adding energy there, we are speaking about leaking in acoustic wave. So in terms of a intensity flux coming in at the boundary, so that is the way we are thinking about adding energy. We are not really speaking about adding energy in a microscopic sense, which yes, for example, if you are adding heat, you would have you would change this adiabatic condition, and then by definition the heat release rate or the heat addition rate to the particle has to appear in the picture. In fact, the amount of acoustic energy added would be the correlation between pressure and heat release, we will show later. But at the moment, so that is like a volumetric driving. So there is a heat release taking place in a volume, and how much is the acoustic energy created in this volume wherever the heat release happens. Flame may be thin, but whatever in that flame zone. But here we are speaking about some wave being pushed in from, infiltrated in, I think that is some word we read in newspapers. So from outside the sound is created, so we are not worried about creating sound itself. Somehow there is something here and you send in here. It could be sound from outside, or it could be a loudspeaker coming in, or the other problem, the way we look at it is we have set up a standing wave, sound already exists, we are looking at how it leaks out. So this question we are sidestepping for the moment, but that is a central question to the course. So when we finish all these things, we will come back to how the heat added to a particle changes the acoustic energy and everything else. Okay, any other question? Okay. So the boundary condition here would be u hat over p hat over rho c equal to y, and I put the script y, which would mean this is non-dimensional admittance, and it is very convenient to work in terms of non-dimensional admittance, as you would see. That is the reason we do, and here it is perfectly rigid, that means u hat equal to 0, and in this companion problem again I have rigid and rigid, so here also u hat is equal to 0, and my coordinate system is such that this equal to x equal to 0, and I would call this x equal to L. So we are solving for the eigenvalue, and let us say eigenvalue of this problem is k, and the eigenvalue here is k naught. And you can already see the conspiracy. We will try to express k in terms of k naught, then some simplification will happen. So we say that k is k naught plus k prime, which is why I started with a rigid plate and then said there is a small departure from that, and then the algebra becomes simple. So if you have a expression, it is easy to explain results, and then you can move to solving a more complex problem numerically, and so on. So I hope the problem is set up clearly. It is a well defined problem. So the pressure P hat equal to, it is a complex amplitude, A e power ikx plus B e power minus ikx, and if you have a rigid end at x equal to 0, then what happens, A will be equal to B, right. So u hat is 0, and u hat would be like A minus B. So you should get P hat equal to 2A cos kx. You can write this as e power ikx, take the A out, so e power ikx plus e power minus ikx, multiply and divide by 2, and then you can call the exponential term as cos kx, and there is a 2 outside. And u hat, can you derive an expression for this? Can you work out and rather than just copy? I will write the answer, just see if you get it. So if you take dp by dx equal to I omega u hat, and from there you can get this. Is this okay? Can you just check if there are any sign mistakes or something? I think there should be a minus. You're getting the same answer? Okay. At L, script y, that is admittance, equal to minus I sin kl divided by cos kl equal to minus I tan kl. Okay. So y, the non-dimensional admittance, consists of real and imaginary part, and we will try to separate out the real and imaginary part. And I will say this k equal to k naught plus k prime, where k naught is the eigenvalue of the corresponding closed duct. K naught is the eigenvalue of this closed duct. So this will be tan k naught plus k prime times L. This could be expanded out as minus I times tan k naught L plus tan k prime L divided by and at this point I have not made any assumptions about what sort of quantity is k prime. So in general it is a complex quantity, and only assumption I am making is that k prime is very small, or the magnitude of k prime is very small compared to k naught, so that I can do the Taylor expansion kind of thing. So both k real and k imaginary would be small compared to the value of k naught. So that is the only assumption that I am making, but otherwise it is in general complex. So now you can see why I made this assumption that or the separation that k is k naught plus k prime. So you can tan k naught L will be 0 because velocity is 0 at this end, and so therefore you can write this as minus I tan k prime L, which I can further simplify as which if I expand out would be minus k real prime times L minus I k prime imaginary times L times I. So this, if I multiply out, would be k imaginary L, this would be minus I times k real times L. I will pause for a moment to let you verify if this is indeed correct, because otherwise the answer would be wrong. Correct, fantastic. So this is y real plus y imaginary. So we can actually write separate formulas for y real and y imaginary. So one second, let me just so we can write this as two real equations, this complex equation, y real in terms of k imaginary and y imaginary in terms of k real. So we wanted to first take a look at the growth or attenuation. So for that we need to look at the k imaginary, right. So k imaginary is nothing but omega imaginary over c times L. So you can get omega imaginary would be equal to y real multiplied by c over L, which we can think of as L over C is like a characteristic time, right. What is L over C? L over C is the time required for a sound wave to traverse through the length of the pipe. So that is a characteristic time tau equal to tau it is a natural time scale in our problem because we have a length L and the sound wave is going. So L over C is the time taken for the sound wave to come in. So if we look at our term e power I omega t, we have written here that e power I omega t was equal to e power I omega real t times e power minus omega imaginary t. So your exponential growth or decay comes straight out in terms of y real. So if y real is a positive quantity, that would mean that we remember from last class that that is, what does it mean? It's energy going from left to right, right? So energy is going from here out, so you should have a decay, and that's what you are getting. And if y real is negative, energy is coming in this direction, and therefore you will have it should be something like a flame which drives, then you have, or a loudspeaker, whatever. So you should be having growth if you have the opposite sign. So is this part clear at this point? So the other question that is still to be dealt with is, what does y imaginary mean? There is a question I think you guys asked earlier, and so you can see the answer by writing it out. So get different colors. This equation k prime real times L equal to minus y imaginary. So k equal to k naught minus this k prime is k minus k naught. So I can bring the k naught to the other side, right? K prime equal to or k equal to k naught plus k prime. So that's what I did. So if you know k prime, you can bring k naught to the other side, except that we are only dealing with the real part here. This would be equal to 2 pi f naught over c minus y imaginary over L. This, and k would be 2 pi f over c. So if you multiply out, you will get f equal to f naught minus y imaginary over 2 pi. Tan theta, if theta is small, goes like theta. So I am assuming that k prime L is small quantity.
But theta, if you say theta is small, that statement makes sense only if theta is real.
No, you can have an expansion of sine theta as what is the expansion, theta minus theta cubed plus theta per phi. That holds for a general complex thing.
But when, like in what conditions will that limit be applicable in complex?
The magnitude of theta should be small, that's all. There is some convergence criteria, I think it should converge. It will converge unconditionally. It surely works for small and there is no restraint on real or complex. The question here is that whether this expansion for tan theta in terms of theta would work for complex numbers, and the answer is it will. Okay, so now back to this. So f, we said that equal to f naught minus y imaginary over 2 pi. So if y imaginary is positive, that means f will come down. That means you can actually pack more waves into it. And if y is negative, f increases, that means fit less number of waves or something like that. I mean, it's not like many more waves, but it stretches that way or this way. So I hope this answers the question, and it stretches this way or that way depending on where exactly the reflection happens. So this is a concern in terms of what is the actual frequency change, but more importantly, if you speak about the growth rate, I think this term tells the whole story. So we can relate the impedance or the admittance of the boundary to what is the standing wave being growing in time or decaying in time. Okay, I think it's very straightforward. Any questions? I will write a general result. So, we well being applied to this particular problem, let us call this as N1 and this is N2. So, this is the acoustic energy corollary, and we will time average this, so that so the triangle bracket would mean implies time average. So, if we do this, let's we can write it of the form e power minus 2 this is 0 because we said at 1 it is a perfectly rigid condition. So, if you differentiate this, you will get times E naught. So, we can write this as 2 omega imaginary equal to y real times pre prime RMS square. Oh, I forgot the area. So, this times A times A divided by E naught. So, you may find this kind of expressions in some books or papers. So, with this exercise I try to tell you the reason why we are interested in measuring admittance of flames and so on, because one thing, the direction would be determined by the sign of the real part of admittance, and also it translates to growth rate or decay rate. Any questions? So, if there are no questions, I wish to move to the next topic, which is acoustic attenuation. We wrote our solution in terms of F and G, and we said acoustic pressure is F of x plus Ct and acoustic velocity is, or F of x minus Ct and acoustic, and that was the right running wave, and there was a left running wave G of x plus Ct, and similarly we wrote expressions for velocity as 1 over rho c times F of x minus Ct minus G of x plus Ct. And by definition, this wave does not change shape, and this is not able to take care of any attenuation of the wave and so on. But in reality, attenuation does happen, and sometimes it deliberately happens. And so since we are in a combustion instability class, let us speak about what would be the practical means to have attenuation in a combustor. So let us think about most of your aerospace students. So we have a solid rocket motor, and it does have solid rocket motors are very prone to instability, and you have to have some kind of countermeasure or some kind of safety against instabilities occurring. And I guess some of you who did the propulsion class would know what is the easiest thing to do to get rid of instability. Add aluminum, and aluminum is added anyway to a solid propellant to increase the performance, because metals give high specific impulse, and so aluminum also burns and forms alumina which is initially molten, and as it goes through the nozzle it may start solidifying. These alumina particles have a certain size and they have a certain drag, because the particles, when they are in a sound field, the particle will try to move along with the sound field, so sound field will drag the particle, and in the process the sound will lose some energy, because when it is trying to drag the particle, that means it is giving some of its energy to the particle or the droplet, and it is giving energy, so it is actually losing and the particle is gaining energy. And if there are lots of particles, if it is like one particle in the sound wave, it probably does not matter, you can think of it as one way coupling, but if there are very large number of particles, the sound will start, the sound wave or the acoustic field will start losing some amount of energy, so it is like now a two-way transfer. So this would lead to acoustic attenuation, and that is what the solid propellant motor designers try to make use of as some kind of insurance or protection against combustion instability. And you must have seen attenuation in some form or the other. For example, if it is raining and you shout, I mean the raindrops will attenuate the sounds, and you will feel that you really have to shout loud. Or if you are attending an open air concert and the raindrops are coming, you would suddenly feel a reduction in the volume. Of course, there are two effects that you hear simultaneously, only the sound of the rain itself, but the raindrops take away, it damp the oscillations. The other example of damping I can think of is if any of you are musicians here, when the music band practices, when they set up the instruments in the concert hall, and they will set the amplitudes at or the amplifier at certain level, and everything would be quite loud, but then they wait for the, so they will set up everything, tune the instruments and make sure everything is okay, and then when people come in and then they start playing and the sound level won't be enough at all, it almost like the volume went away somewhere, so the people and their clothes are damping, so they take away the energy, so actually you have to jack up the amplifier once the people come in. So there are a lot of ways you can, a lot of places where you see damping. You see in concert halls there are special panels like we have here in the studio. You see these panels, they are meant to damp, because these holes, they actually absorb the sound and take away some energy from the incident sound field. So there are a lot of damping. So we will not look at a general case, but we will look at attenuation happening to one dimensional waves, standing waves, and we will see how this can be studied. And a simple way to think of it is, if you have a tube filled with pebbles or something, or packed bed. Some of you with chemical engineering background would know what is a packed bed. Packed bed is nothing but a column in which a lot of packings. Packings are like material, like pebbles or something, but they have the good packings have high void fraction. That means a lot of free space, and they are made to improve the contact between let's say two fluids or something like that. So let's say you can think of a tube filled with foam or packing or something like that, and that would be a good good example for a 1D attenuated traveling wave. Or you can, other example is to think of a droplet laden gas inside a tube. Okay, attenuation will depend on the medium and its properties, and sometimes the flow that is set up, and even if there is nothing inside, there will be attenuation, because the molecules have vibrational relaxation and so on, and they take away the energy. So for example, I mean, if you have a simple tube, even in that the air itself will absorb, and in fact you would notice that on humid days there will be more attenuation compared to days which are dry. So we will not speak or go in detail about what causes attenuation, but we will describe attenuated wave. I think I will restrict my objectives just to describe attenuated wave and describe how the amplitude variation is, how the phase variation is, but then the attenuation itself is dependent on the physical phenomena. For example, if it is a droplet laden gas, like in the case of solid rocket motor, then it is related to the droplet's properties, and the size of the droplet, for example, certainly affects the drag, right, through the Reynolds number and so on, and the frequency will come into play, because the time scales involved are there. So now the Strouhal number, Reynolds number, Stokes number, those numbers will come into play. In fact, when you use when you try to design a solid rocket motor, ideally we would like to adjust the aluminum size such that the alumina droplet size would be the correct size needed to damp the oscillations. For every frequency you would need a certain particular droplet size distribution to damp the oscillation. So ideally good designers, I do not know whether they will work with the equation or they go by feel, but they will actually tweak, this is one parameter which is available for tweaking, and that is why whatever works for a rocket of a certain size may not work for a rocket of another size. For example, if you have a rocket of certain size, let us say 10 meter, and you everything works fine, and the same rocket with the same propellant and same diameter you just extend into double, and then suddenly it may develop, there have been cases where it suddenly gives instability, and that is because the droplet size was just fine to kill the earlier frequency. Now the frequency has come to be a lower value, and now this aluminum size that you have, which results in certain alumina size, droplet size, that is not tuned to attenuate frequencies in this big motor, or vice versa. So yes, this is an important thing, and I will not attempt to model that aspect, but I will talk about a description of the standing wave in presence of alumina, or in the presence of particles or drag. So if there is attenuation, how will the wave look like, what will be the structure. Now doing that, connecting that attenuation to your specific system depends on the specific system's properties. I hope it is clear. I gave a very long answer for a short question, but it is a tricky point. We can discuss in private. I have worked out some such problems in the past for my research. Now yeah, I forgot to mention another case where attenuation is very important is when you are talking about propagation in narrow tubes or narrow ducts. For example, in thermoacoustic engines, thermoacoustic engine is a device where you use a temperature gradient across a thing called stack, which is a set of plates, and use that to drive sound in the engine. So in that, the stack has small plates which are narrowly spaced, so their attenuation is quite important. So in general, when you have a narrow ducts, attenuation gets very important. So we will study this in an idealized geometry, and a good description of this is given in the textbook by Kinsler and Frey. You have I and R. I is the incident wave, R is the reflected wave, and let us say we have some kind of sound source here. It can be a piston moving back and forth or a loudspeaker or something like that. So let us for the present assume that we have a perfect termination or a perfectly rigid termination. That means the amplitude of the incident wave is equal to the amplitude of reflected wave. In the earlier problem we saw A minus B equal to 0, A equal to B, that kind of situation. So the sound source supplies the acoustic power which will be consumed in the acoustic absorption. So we will look at such a case. So we will not look at a complex omega, we will set up a real omega. That means there is a sound source and we have crossed the transients and we are reaching some kind of steady standing waves, stationary standing waves. So there will be no growth or decay of oscillation, that means omega can be chosen to be real, but we will look at the wave number which can be complex. That means the wave in the standing wave you will not have same maximas for all the maximas, that can be growing or decaying, and that will count in terms of wave number. Let me write these things down. but we will have a complex k, we will have a complex wave number. So we will write this complex number as something real plus something imaginary. So let us call the wave number is k tilde, which is k minus I alpha, and it will be clear why it is convenient to choose such a form. So now we will think of how to write the expression for the standing wave. So we will write it first for right running wave and then for left running wave. So that must be of the form p naught e power I times omega t minus k tilde x. Now I will substitute this expansion for k tilde, so this would be p naught e power I times omega t minus this would be p naught e power times minus times minus is plus, I times I is minus 1, so this would be e power minus alpha x. So this is a right running wave. So when a wave is running to the right, it should decay to the right. Left side should have more amplitude than right side, and that's, so we will assume alpha is positive, and then this description looks good for a right running wave. Now we will have to look at a left running wave in the same manner. Use another color. So it will be it will go like p naught e power I times omega t plus k tilde x here. So this would be p naught e power I times omega t plus k minus I alpha times x. So this would be p naught e power I times omega t plus kx times e power I times I is minus 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 e power alpha x. So a left running wave is what is described here. So it will appear as if it is growing, but if you think about a wave going from right to left, it is actually decaying. So this decays to the left, this decays to the right, so it is a little tricky. So the total pressure can be written as sum of these two things. This is the total pressure. So I will give you some homework at this point, because I do not think I will have time to complete it. We can look at it next class. So first thing would be derive an expression for the pressure amplitude distribution. So and you hat, and second thing would be make plots, and I will show you some sample plots now. So over here is would be a plot of pressure amplitude versus distance. When you write kx, it's non-dimensional because k is wave number, and this would be the plot of phase. So please try to calculate this. I have done it using Excel, which is quite simple, but you can write your program in Fortran or C or MATLAB or anything of that sort and try to plot. And this is how the acoustic velocity would look like, and I have again normalized the velocity and pressure with their values at x equal to 0. And last thing, try to see if this interpretation of phase agrees with what you think, because if you have a sound source here and energy is coming to it and the left running wave is decaying, and so eventually it will come here, and then what is going here will also start decaying as you come here. So in near the sound source here, it will almost be like a traveling wave, because you had a wave, left running wave coming here, and then it reached here and it lost a lot of its amplitude, and then it starts coming as a right running wave, and it's again continuing to get attenuated. So here it will be predominantly a left running wave if it is damped well, and as you come more towards this, you will have both of them coming, and then the phase should be such that we have to look at the phase. So the particles here should vibrate first before the particles here are moving, so because the energy flow is in this direction. So we had some intuitive way of understanding how the phase relates to the direction of intensity flow, and see if this is consistent with that, and please do this at home, then we can discuss this tomorrow.